Okay, this will be the review of the parent functions and their properties. So we had a list of a bunch of different parent functions: linear, quadratic, cubic, all those properties, domain, range, asymptotes, where increasing, where decreasing, symmetry, even, odd, neither, all that good stuff. And then operations on functions, so adding two together, subtracting, multiplying, division, composition of functions where one gets plugged into the other, which kind of led to inverses. And then finally, linear regression from data and transforming if there was a better model than a linear model, generally with using logarithms at this point. So let's go over the problems that were the review problems. And they may, the ones that you guys did in class may have had the choices scrambled around. There were different versions, but this will cover the topics at least. So question one, we want to just be able to tell just by looking at the shape of the graph there, so that one, we can see it kind of starts at a point and just rises in one direction. That's actually the square root function. Um, and if you recall, the parent function would actually start at the origin and kind of do something like this. Maybe not quite that steep, but it has that shape to it. And just be careful, it's not a logarithm. That's kind of the commonly confused one. The logarithm graph would actually, the parent function for log x actually it's similar, but it actually continues down all the way. And sometimes in your calculators, it looks like what is shown on the paper in blue there, like, because it doesn't show that it continues down. So if you were to just be kind of trial and error using a calculator and graph log of x or ln of x, it would look like the blue one in number one, but technically the log one would continue and the square root one is the one that starts right there. Okay, so square root function there. The domain of the function as shown. Okay, so not the parent function, but of the actual function shown. The domain is again asking what x values does this graph go through, and it's important to note where it starts. Okay, it's starting right there. So that x coordinate there is -3, and this graph is going to the right, so it's going through all numbers that are greater than or equal to -3. Okay, or that could be written in interval notation as it actually starts at -3, so a bracket -3 and goes to positive infinity. Okay, so that would be an equivalent way to write that. Similarly, the range of this function, where it's starting, again, remember the coordinates down here are going to be -3, -2. So the y values start at -2 and then gradually just increase and increase and increase. So the range would be all y's that are greater than or equal to -2. Okay, and similar interval notation would be from -2 to infinity. Okay, so now which equation could represent that? So we need to think about the parent function would have started again at the origin. So that's kind of like the major point on this graph is where it started. So if normally it would start at the origin, that point has been shifted, looks like to the left 3 and down 2. Okay, so I definitely, I think the down 2 can be seen as a -2 on the outside there. So I guess it eliminates option B at least. Now the issue is which one is going to shift us to the left 3. And the issue is that a left or right shift has to be done inside the function. Okay, and this function happened to be, again, the parent function was the square root of x. The square root of something. So inside means that 3 needs to be inside the square root symbol. Okay, it's not necessarily all about parentheses. I know that's kind of a common misconception because this one doesn't even have any parentheses, but inside the function in this case means under the square root. So since it went to the left 3, anything inside is like the inverse is what you might think. It's kind of the opposite. So I'm going to need an x and I'm going to need a +3 inside to get a left shift. And then the -2 on the outside of the function, not under the square root. Okay, so the answer to this one should be C. Okay. All right, moving along, doing some operations on functions. Okay, so we're looking at number 5 here, 2t to the q to the third plus 2, and we want to find h of -2. So that means basically that -2 is going to go where the t is. So h of -2 will equal 2 times -2 to the third plus 2. Okay, and then it just becomes an order of operations problem. -2 to the third power, so -2 times -2 times -2 again, so I believe that's going to be -8. So 2 times -8 plus 2, and that will get us -16 plus 2, which is -14. Okay. Other option on problems like this is just plug the equation in the y equals screen. Just plug in 2x to the third plus 2 and go to the table when x is -2. You know, if it was a little bit messier, that might be a good option. Okay, number 6, we are asked to find a new function, which is going to be the sum of the two. So we are going to basically just think of it as g of t plus h of t. Okay, so if we carefully just write that out, g of t was 3t minus 2, and we are adding h of t. And since it's addition, I don't really even need parentheses. I'm just going to put these in here, negative t squared plus 2 plus t, and we are just going to combine like terms. Okay, so you might want to just be careful that I don't really like how the plus and the negative sign are written there, so that you might want to just clean up a little bit. And this is really going to boil down to 3t minus 2. This plus and negative is really minus t squared plus 2 plus t. And then we will combine the like terms, and we usually like to write them in descending power order. So I'm going to write the negative t squared first. Okay, so that one's accounted for. Combine the 3t with another t out here, so plus 4t. And then the minus 2 and the plus 2 actually cancel each other out. Okay, so negative t squared plus 4t. Alrighty, number 7 and 8. Here's our composition. Okay, again, that open circle is g of f of 3. So you can think of that, and I actually prefer to think of it as written this way. Okay, so that is the exact same thing as writing it that way. It's not a multiplication, it's an open dot there. Okay, so we need to find first, we always work on the inside, right? So I need to find f of 3 first. Let's find out what this equals. So f of 3, the rule just says it is 4 times, let me just make sure I can't really read that. 4 times 3 minus 1. Okay, so that looks like an 11, right? So f of 3 is 11. So that is what's going right here. F of 3 is 11, so we're going to now find g of that. So I'm basically taking this answer and plugging it into g now. So g of 11, the rule for g is 2 times the value plus 5. Okay, so 22 plus 5, 27 for that one. Okay, so that was composition of functions when given a specific value. Number 8 is composition of functions, but for a general value. They're not telling you what to use for n here. So again, I would think of this as g of h of n. Okay, and our first job is to just replace the inside function. Okay, it's not going to be a number this time, but we still know what it is, right? We still know they told us at the very beginning what h of n was. So we are really doing g of h of n was given as n plus 2. Okay, and now I'm just going to look at the rule for what G wants us to do. And G basically says, let's get a color here. Here's the rule for G. G of anything is negative 4 times the thing plus 4. Right, so this is going to be negative 4. This n plus 2 is becoming that n now. And then there's still a plus 4 on the outside. And we will just do our little simplification here. So negative 4n distributing, right? And then minus 8 n plus 4. So negative 4n and a minus 4. Okay, then moving to the back with our data and linear regression and transforming the data. So this one, they gave you a scatter plot, and they actually gave you the equation from the original data, and they gave us the R value. Okay, so there's a plot shown too. So which of the following best describes the linear relationship? So you can either tell by looking at the actual scatter plots, very curved, right? Doesn't look very linear, but it's better to use that R value. So that since the R value is negative, we know it's a negative relationship. And since it's 0.44, that's pretty weak. Okay, remember we consider 0.8 as kind of the borderline to be strong, and then 0.5 to 0.8 is kind of a moderate. So this is on the weak end, um, weekend. um, so this would be a weak negative correlation. Okay, if it was a multiple choice and you said moderate negative, I would be okay with that too. All right, so what is the best prediction for the heart rate of a mammal with a mass of 200 grams? Okay, so we have this linear equation. At this point, that's the only equation we have, so that's what we're going to use. Um, so maybe we should be kind of clear using the linear equation, because we'll see, I think, in a minute here that the linear is not the best, but at this point, that's what I was wanting you to use. So what we would need to do there is take the 200, that's an x value, and it's just going to get plugged in for x into the equation. Okay, and you can just calculate out the value there using your calculator, and we can get the closest answer there. And in this case, it turns out to be around 177.7 beats per minute. Okay, so number 11, based on the shape of the data in the scatter plot, what transformation? So this one definitely has curves, okay, and curves are usually related to exponentials or logarithms, or power functions, I should say. And the way to deal with an exponential or to kind of undo it is by taking logarithms. So that's kind of the common transformation that gets done here. So if we were to take the log of the x and the y values, that would hopefully straighten out this curve and make our linear model a little better. Okay, so that's kind of what we've been doing in most of our examples. But now, how do we actually get the equation? Okay, so let's see number 11 or 12. After taking the log of x and y, a new linear equation, so let me jot this down. So y equals negative 0.277x plus 2.34. Okay, so that is the linear equation after we've taken the log of both. So this y and this x in this new equation is not the original y and x from this equation. Okay, so they're different, and that's why the numbers are different. So our goal is, can I turn this into a function that goes back to being about the original data? And we can, as long as we think about what we did. This was really the log of the original y, and this other one was actually the log of the original x. Okay, so I'm just replacing x with log x and y with log y, and that plus 2.34 was still there. Okay, and now what we want to do is solve this thing for y and get a new equation. Okay, so there's a few steps involved. So let's first start out. We want to get the logarithms on the same side of the equation. So I'm going to add I'm going to add this to both sides. So it's going to be plus 0.277 log x. It's going to equal 2.34. Okay, so again, that was just adding this to the other side. Get the logs on the same side. Then we have a couple of log properties we can use. One of them stated that if you have a coefficient out front, that it can become the exponent on the thing you're taking the log of. Okay, and that was kind of that power property. So this is basically log of y plus the log of x to the 0.277 power, still equaling 2.34. Okay, and then we said if we had two logarithms being added together, it can be condensed into a single logarithm of the product. So it's the log of y times x to the 0.277. Okay, and that was just that product property, because again, logs are exponents. So in the red step, we were kind of adding exponents. Okay, and if you remember, we add exponents when things of the same base are being multiplied. So adding logs is basically like a single log being multiplied. Okay, and now what we want to do is kind of simplify even more. I want to get that log out of the equation here, because again, I want to solve for y. So here's what we got to think about. The common base here is 10. So I'm going to just change forms on this, and any logarithm can be changed to an exponential. It's the base to this power equals the stuff you were taking the log of. Okay, so the logarithm is now at least gone, which is good. And now we just got to do a couple calculations and a little algebra here. So 10 to the 2.34 power is just some number. Your calculator can do that. So let's see what that is. 10 to the 2.34. Okay, so that's around 218 point, let's go 218.8. Okay, so this side just 218.8, just a calculator problem. And that equals y times x to the 0.277. Okay, now we want to solve for y. I'm going to divide both sides by the x to the 0.277 power. So I will have 218.8 over x to the 0.277. That's going to equal y. So we have solved it for y. Now there's one more step. Usually we don't write it as a fraction like that with an exponent in the denominator. I guess you could, but we're kind of more used to having it be y equals something times x to a power. So the rule here, if you have an exponent in the denominator, that's like having a negative exponent. So this would really be like 218.8 times x to the negative 0.277. Okay, and that would be your power function. Okay, and if you were to check and graph that, it would actually fit the original data much better than the line did. Okay, let's just make sure our answer choice shows up there. Yep, looks like option B for that one. Okay, so make sure we understand those properties. You know, there's a few steps to go. This was the one also if you were fortunate enough to have the original data, like let's say I give you a table of the scatter plot, you could actually go into your calculator and do a power regression and verify that this really was the power function. But if you don't have the original data, okay, which is kind of a way to make sure you know your properties, these are the steps to go through. All right.